As geotechnical and structural engineers work to better understand the survivability of different building types under seismic loads, a key frontier of study is deep foundations. This study, the first of its kind, sought to better understand the performance of helical pile deep foundations under earthquake conditions. Computer models predict that helical foundation components will perform well under seismic loads, because the shaft of the pile is relatively slender compared to other foundation types. The predictions show that this slender aspect ratio helps to dampen the destructive harmonics of the earthquake, which means that less of the shaking energy is transmitted to a supported structure. In addition to these computer models, field observations of helical pile performance during earthquakes in New Zealand and Japan have added further proof that helical piles might be the answer to foundation design challenges under earthquake loads. During the February 22, 2011 earthquake, Christchurch, New Zealand was damaged by a tremor which registered at 6.3 magnitude. Due to the soils in the area and the shallow focus point, some areas of the city were devastated by a peak ground acceleration of almost 2 times the force of gravity. This peak ground acceleration, one of the most powerful ever recorded, severely damaged or destroyed many buildings in downtown Christchurch and caused the tragic collapse of the CTV office building, killing 115 people. A post-earthquake survey found that all buildings constructed on helical piles survived with minimal structural damage, adding to the qualitative proof that helical piles perform well as foundations in active seismic zones. However, until now, no empirical studies had been undertaken to validate these anecdotal observations. Dr. Amy Serrato, a helical pile researcher from the University of Oklahoma, has come to the University of California, San Diego to test these questions on the largest outdoor shake table in the world.
Well, we are standing at the world's largest outdoor shake facility. The table has a 4 million pound payload, and as you can see, we have the laminar soil box on the table, on the platen, and it is 15 feet tall by 22 feet long by 10 feet wide. And so we have 10 helical piles that we installed, and we're going to test them seismically to see how they react to earthquake loads. And right now the crew is loading on the inertial weights, which will simulate a building load on top of each pile.
Piles of several types and sizes were tested, including round and square members, plus a push pile to compare with the helical piles. To measure the shaking forces and resultant deformation of the test subjects, the team fitted accelerometers and strain gauges to the test members. The sensors and the wires to control them were carefully threaded into the pile members and protected with epoxy to prevent damage during the installation process. All sensors were then connected to recording equipment which captured the millions of data points collected during the test. To simulate independent axial loads on the pile members, on-site contractor Torxil bolted cylindrical concrete weights onto each pile. During a later test, a sand skid was used to simulate a building supported by a group of piles. All tests included a simulation of the 1994 Northridge earthquake and the 1995 Great Hanshin earthquake in Japan.
Northridge 100% T0 in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, running.
Both seismic events caused extreme damage to structures due to very high acceleration forces at the surface.
100% T0 in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, running.
I think it went very well. It performed exactly like we thought it would in the analysis. Everyone was telling me that all the weights were going to bang together and everything was going to shear off, but our analysis said that the helical piles were going to behave a specific way, and thankfully everything went as we planned. There was a lot of displacement of the soil around the piles, but that's exactly what you would expect to happen in the real world. And this test is actually a good one to show that even though we hit the piles with a 6.9 earthquake, we came back and hit it again with even bigger earthquake. So for aftershock effects, these helical piles held up very well. So pretty much it took 7 earthquakes today and nothing failed. So we're very pleased with the results. So what we'd like to do next is instrument full-size piles that are going under an actual building in a seismic zone. So we have a project coming up with Pile Tech in New Zealand to go over there and instrument some large plate piles and install them underneath an older historic University of Canterbury building. And then we can be able to monitor the pile behavior during earthquakes. So it'll be a continuous monitor that we can access all over the world to understand how those piles are reacting during an actual earthquake under an actual building. And I think that's the kind of data that we still need to collect, because no one actually has data on any type of foundation system in a real earthquake. That's just starting to become important to people, and we hope to be on the leading edge of that.